Let's go through the last two practice questions from our Unit 4 Part 1 notes. So we had started the first reaction. We just have to draw the reaction coordinate diagram and propose a change to the nucleophile or electrophile. So tasks 4 and 5. And then we'll look at the other reaction as well. So just to remember, we were given all of this information right in here, the starting material and the solvent, which is the nucleophile. We drew the mechanism. Well, first we determined that it would be an SN1 mechanism because the alpha carbon, the carbon bonded to the leaving group, is tertiary. So that would make SN2 very difficult or very slow for the nucleophile to bond at the same time that the leaving group leaves. It is more likely for the leaving group to leave, form a tertiary carbocation, and then the nucleophile bonds to the carbocation. We finish the reaction with a proton transfer to neutralize the final product. We get this alcohol product. We drew transition states, one for each step. So this is transition state 1, the leaving group leaving. This is nucleophile attack, and then this is the proton transfer. So let's draw the reaction coordinate diagram. I'll do that right over here. All reaction coordinate diagrams are set up similarly, where we have energy on the y-axis. That can be E for energy, it can be G for Gibbs free energy, some energy unit. And then reaction progress is along the x-axis. So in this reaction, we have 3 total steps. We have carbocation formation, nucleophile attack, and proton transfer. That means that we will have 3 transition states. We have 2 intermediates. I'll go ahead and label the intermediates. These are observed molecules, but they're not the starting material or product. So this first group here is an intermediate. And then the second molecule, or I guess third, is also an intermediate. So when drawing the reaction coordinate diagram, we need to show both intermediates, we need to show all 3 transition states, and then reactants and products. I did say also, just to keep this in mind, we're going to assume the reaction is exothermic. So let's just set up where everything's going to be. I'll start with starting material and product. I put product lower energy than starting material because it is exothermic. I actually think I'll move this over a little more so we have space for all 3 steps. Then we form 2 intermediates. So let's put those in. We know that the first step of SN1, the carbocation formation, is rate determining. That forms the high energy intermediate. So I'll put intermediate 1, high energy, or higher than intermediate 2. So just labeling these intermediate 1, intermediate 2, intermediate 1, intermediate 2. Okay, then I think at this point, I prefer to draw in the actual line to show energy change throughout the reaction. First step being rate determining means that this will have the highest energy transition state. So this is TS1. And then we have another activation energy for that second step. This is where TS2 will be. And then a little bit of activation energy for that last step, which is TS3. It is important that this is highest energy. Let's see, I'll label in pink. because this is the rate determining step, RDS, rate determining step. So that will have the highest energy. This is step 1. Step 2, we have another transition state that's higher energy than intermediate, but lower energy than transition state 1. And then same with transition state 3, higher energy than intermediate 2, but lower energy than the other transition states, especially transition state 1. We haven't talked about the energy much of proton transfers, but these are really low energy, or they require very little energy for that step to occur. If you had put transition state 3 about equal energy as transition state 2, that would be fine, as long as it's lower than transition state 1. In reality, it is much lower, doesn't require a lot of energy for that proton transfer. Okay, I think that is everything for the reaction coordinate diagram. The last thing we need to do is propose a change. So I'll put this down here. The question was, just to go back and review, propose a change to the nucleophile or electrophile that would increase the rate of the reaction but produce the same product. So we want to make sure whatever we change, we're still going to end with this final product. One thing that we can do is change the leaving group. Since the leaving group is not part of this product, oh, by the way, I should note that this is the desired product here. This is a byproduct. Let's label that. But really what we're working towards, what this reaction is working towards, is the substitution product. So this is what we don't want to change. So if we change the leaving group to a better leaving group than bromine, that will help the reaction proceed a little faster. The leaving group that we know is better than bromine is iodine. So we could change the leaving group to iodine. And that would be the best change for the nucleophile, or sorry, for the electrophile. We can't change any of these other carbon groups. We can't change any of these because then that would change the final product. Okay, next, another option is to change the nucleophile. It is currently water H2O, but based on our notes, something that would help this move faster, but still add an OH group in the product, is changing the nucleophile to hydroxide, OH minus. That's a better nucleophile. It is more likely to give away electrons. So based on what we've learned so far, that would be a better nucleophile for this reaction. You might see hydroxide listed as like KOH or sodium hydroxide. We just have to remember that potassium and sodium are spectator ions. They're just cations, so that hydroxide charge is balanced. That's like how we would find hydroxide as a solid. Okay, this is everything for reaction 1. Let's do reaction 2. Let's see, let me move this up so it's not in our way. Okay, so looking at reaction 2, the first thing we need to determine is if this is going to go through a SN1 or SN2 reaction. If we identify the leaving group, we have bromine there. That makes this the alpha carbon. This carbon is bonded to 2 hydrogens and 1 other carbon. So I'll write the note over here. Alpha carbon is primary. This means that SN2 is more likely. If this alpha carbon lost the leaving group, it would form a primary carbocation, and that step would require a lot of energy that it's unlikely to occur. It's more likely that the nucleophile will just bond directly to that alpha carbon at the same time that the leaving group leaves. So this is our electrophile molecule. This is the nucleophile. We have one atom in here. The oxygen has lone pairs that it could give away. Okay, let's draw the mechanism. So I'm just going to copy down electrophile and nucleophile. And then nucleophile, let's draw out the bonds here. So we have oxygen bonded to a hydrogen and then a CH2CH3. So just drawing out the bonds to oxygen, since that's the atom with lone pairs, that's what's going to be involved in the reaction. SN2 reaction happens in one step, so we have nucleophile bond to the carbon and leaving group leave. Oxygen still has one pair of electrons, and then it now has a positive charge. And then we have Br minus. So this is step 1. This is the SN2 reaction. Now our product is charged, this main organic molecule, the carbon, hydrogen, and oxygen molecule. So we can neutralize that charge by using bromide again. Take the hydrogen, proton transfer reaction, oxygen accepts electrons. So these are our two products. HBr is a byproduct, and then that larger organic molecule is the main product. This is our second step, which is a proton transfer. And if you work better, visualize molecules better as skeletal structures, I'll just draw what this is as a skeletal structure. We have 3 carbons and then an oxygen with the isopropyl group at the end, and then CH2CH3. Could draw the molecule like that as well. Okay, so that's our reaction, SN2 reaction step, and a proton transfer to get that final neutral product. I will box this product just like I did for the previous reaction. So we can keep in mind that was our desired product. Okay, let's do transition states next. We have 2 steps, so we'll have 2 transition states. First transition state, we have the nucleophile bonding and the leaving group leaving. Remember, we need to draw these as opposite each other, happening on opposite sides of the carbon. So let's see, if we keep all these atoms where they originally are drawn, you could kind of shift everything around if that is helpful for you. I will show the hydrogen bonds. Show the bond breaking to bromine, and then 3 lone pairs, and then bond forming to oxygen opposite of the bromine. We have 1 lone pair on oxygen. The other lone pair is represented by the partial bond. So far we have the structure. We just need to add partial charges. The bromine started off as neutral, and then it became negative. So in the transition state, partial negative. The oxygen was neutral, and then it became positive here. So in the transition state, it has a partial positive charge. And that's our transition state for step 1. Transition state for step 2, we have a proton transfer. I'm going to use skeletal structure just to simplify it here. So this is the CH3 to CH, the other CH3, CH2, oxygen, CH2, CH3. This has, that bond is going to break, so this is a partial bond. And then this also has a partial bond to bromine. Oxygen has 1 lone pair, bromine has 3. The 4th one is represented by the partial bond. And then as far as partial charges go, oxygen was positive and became neutral, so partial positive. Bromine was negative and then became neutral, so partial negative. And that's our transition state for step 2, the proton transfer. Let's draw reaction coordinate diagram next. I'll have to go to the next page. So again, energy on y-axis, reaction progress on the x-axis. Again, we can assume that this reaction is exothermic. And we have 2 steps. So if we just start by drawing starting material and product, product is lower energy than the starting material. We have 1 intermediate here. So on our reaction coordinate diagram, we can put the intermediate between starting material and product, higher energy than both. And then we can draw the energy graph to connect all of these. So starting material goes through transition state 1, forms the intermediate. Then we have a proton transfer, which has really low activation energy, and that forms the product. So here we have TS1, TS2. This shows step 1, and this shows step 2. And that's all we need for the RCD. If you're asked to label activation energy, there are 2 spaces where you can label that. I'll use purple here. That would be between transition state 1 and starting material. This is activation energy for step 1. Between transition state 2 and intermediate, this is activation energy for step 2. If we were to put in delta G, also that would be the difference between starting material and product. Or delta E, sometimes that's E for energy, G for Gibbs free energy. Either one is okay. Okay, last thing is a proposed change. Same as the previous reaction, our leaving group here is bromine. We can always change that and not affect the final product. So if we change bromine, the better leaving group we know of is iodine. So change leaving group to iodine. And again, very similarly, we still need the final product to have this OCH2CH3, this ethoxy group. So the nucleophile, the only thing that we could do is remove the hydrogen and make it ethoxide. Again, based on our notes when we were talking about what makes something a better nucleophile, if it has a negative charge compared to its neutral counterpart, then that will be a better nucleophile. And then same thing, this would be provided as like potassium ethoxide or sodium ethoxide. Basically the ion with a cation, a spectator cation. Okay, that will be all for this section of the notes. We'll begin Unit 4, Part 2 when we come back to class.